Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Here is hostless Ryan Williams, so I am the stand-in host. And Ryan is an intern with us from CMU. He's going to be talking about two CSP applications.
Thank you. So yeah, this is work from a paper I had in iCal. So you can find the paper if you Google.
Or if you want to
Right. Yes. Actually, I haven't. Because Google really ranks me high, you see, but MSN, I don't know. For some reason, people in athletics who are named Ryan Williams have higher priority. I don't know why. I can tell them to make me the first hit. Really, I mean, because this is influencing my decision, you see. All right, so our problems of interest are constraint satisfaction optimization. So we have n variables, each over some finite domains. I will just assume, for the most part, that these domains all have the same cardinality, and they have constraints. So these are functions from the set of domains to 0, 1, Boolean constraints. So the problem is we have a collection of constraints, and we have some specified domains, and we just want to find some tuple of settings to the variables so that the number of these constraints is minimized or maximized. Okay, we'll focus in particular on two CSPs. So each constraint C is just a function dependent on two variables. Call these max2CSP and min2CSP. And the examples, well, are just very numerous. I mean, many graph optimization problems can be solved in terms of this framework, including max cut, k coloring, MIN-BISECTION, max 2-set. So
there are 20 values, one new value is larger domain, and make out of the 20 CSP and 2 CSP.
yes. Yes, the point is that if the domain is small, then the algorithm will be good. So the algorithm runtime, right. So the minimization and maximization problem, certainly the satisfiability problem is the case. The minimization and maximization problem. But anyway, yeah, so the algorithm will depend on the fact that the domain sizes are small. So, okay, that's the problem we're going to look at. Now, how are we going to solve it? We're going to solve it with improved exponential algorithms. So suppose we have a hard problem pi, and its witness size or solution size is some s of n on n-bit instances. And so 2 to the s of n is the runtime of brute force search. And so we'll say that an improved exponential algorithm will be one where we find an algorithm with some epsilon, 2 to the epsilon s of n. So this is exactly what we mean by improved exponent. Some motivation for studying these kinds of algorithms versus, say, approximation or even polynomial time algorithms. So sometimes, obviously, approximation doesn't suffice, depending on the application. And in some cases, an exponential algorithm will actually be a better choice if the instances you have are small, and this is disregarding any constant factors there might be. So if you had improved something that was sufficiently improved in exponential, then it might actually work really well in practice. And they're also interesting theoretically. So for a SAT, is there some, I mean, does it have some kind of, the general SAT problem, does it have algorithm in this form? It's not known. So something like 2 to the epsilon n, where n is the number of variables. So we don't really know the limit to such algorithms for NP problems. And so studying that is just interesting in itself. So complete problems for exponential time would obviously. Okay, so here are some of the algorithms that have been developed for various problems. So there's an algorithm held carved also by Bellman for traveling salesman or salesperson in the 60s. Runs in 2 to the n time, where n is the number of vertices. So this is better than in factorial, much better. So for independent set, vertex cover, really equivalent in this setting. The best known is 1.2 to the n, roughly. This, here n is the number of vertices. For a subset sum, knapsack partition problem, there's an algorithm that runs in like the square root of 2 to the n, where n is the number of items here that you want to sum up. For KSAT, there's been a really long line of work, lots of papers on it, mainly focused on solving 3SAT. The best known, I think, right now is like 1.3 to the n. And this is Soda paper from 2004. And 3 coloring is something like 1.3 to the n. So there's been a lot of work on these kinds of algorithms. So what's missing from the list of problems that don't seem to admit such algorithms is problems like max sat and max cut. So, and that's not for a lack of trying. People have given some algorithms for this, which in some situations are better than trying all the possible cuts, say, or all the possible assignments. But all of these time bounds are of the form c to the m for some constant c less than 2. But m here is the number of constraints. So for max cut, it's the number of edges. So if you have a sufficiently dense graph, then these algorithms are still no better than brute force search. Well, at least in terms of what we can prove about. So another thing is, well, I mean, in the title it says something about matrix multiplication. Okay, and these algorithms don't use matrix multiplication. But why should it be that I have to use a different technique to solve this kind of problem other than the ones that have been used? Well, the intuition is that all the citations above, they either have algorithms that are something like a branch and bound algorithm or a local search algorithm. And what do I mean by this? So branch and bound, just very roughly speaking, is we pick a variable and a value for it somehow in polynomial time. We reduce the instance under this kind of constraint, under this setting. We stop when the instance is good enough for what we want. And then if we get something that's just a dead end, we start undoing variable settings. And in general, this is just sort of like a high-level description of what branch and bound is. So in terms of like max cut or max 2SAT, so what value should we set to the variable? The thing of it is, I mean, it's NP hard to determine what the fraction of satisfied clauses is or cut edges is. So we don't know which clauses are edges, which clauses should be satisfied, or which edges cross the cut. So it's not really clear how to get a bound with branch and bound that will be less than 2 to the n. In terms of local search, so one picks an assignment for all the variables, And you change single values in the assignment according to some measure until the assignment you get is something you want. So the reason why local search doesn't seem to work very well is we don't really know when a local optimum would imply a global optimum. And furthermore, under a certain black box setting of classical local search, it's been shown by Khanna, Motwani, Sudan, and Vazirani that actually you cannot approximate max 2 sat better than 3/2, even with 2 to the low of n times. So, yeah, so you can't even approximate in sub-exponential time. So, anyway, that's some intuition as to why the techniques people have been studying don't seem to work. So what is our approach? Sort of dynamic programming. So in dynamic programming, you usually start by solving all the possible really tiny subproblems. And then you build up. You merge these subproblems in some simple way. You get slightly larger subproblems than you had before. And you iterate until the problem you wanted was solved. So held carps to the n traveling salesperson algorithm has this form and can be thought of as branch and bound with memoization. So I am branching, I'm trying to determine whether or not vertex will be in the current path I'm looking at, and I save all of the information that I learned. So you can think of it, dynamic programming sometimes as branch and bound with memorizing all the answers you see. So our approach is to look for algorithms of the kind of form is to lay out all moderately sized subproblems, roughly speaking, and then merge these subproblems in an interesting way to solve the problem. I guess the main difference is rather than merging in some very simplistic way, you merge in some, like the whole complicated part of a dynamic program is just in the merging of the subproblems. So this will all be clear as I describe what the algorithm is. So here's the main result. If we let K be such that a triangle detection in an unweighted n-node graph is solvable in n to the kappa time. So trivially, we can get kappa is at most 3. Right? We'll show that kappa is actually at most omega, where omega is the matrix multiplication exponent over rings. So you have a graph, you just want to determine whether or not it has a triangle. And this can be done in the omega time, where n is the number of vertices. So, okay, we call m is the number of constraints in some 2CSP problem, n is the number of variables in a 2CSP problem. So if we let D be the maximum cardinality of any domain, then the result is that max 2CSP and min 2CSP are solvable in poly m times D to the n times kappa over 3 times, okay? Moreover, you can actually count the number of optima in that same time modulo some polynomial factor. So you add some polynomial factor on and you'll get the count of how many optima. So because omega over 3 is less than 1, we have something which is an improved exponential, because the brute force search would just be d to the n.
If one gets a smaller matrix multiplication,
Yes.
then simpler. So
Yes. Yeah, you know, it just uses a matrix multiplication algorithm as a black box, right? Just some fixed ring. So if I have a ring R and I have a matrix with elements from R, how fast can I multiply these two matrices? That's the question. And for any ring, for any fixed ring up front, that can be done in omega operations, ring operations. There exists a ring? No, that would be a lower bound for matrix multiplication. To produce some ring, so there'd be a lower bound for matrix multiplication over rings in general. To produce some ring so that this is over all rings you can get that many ring operations. So if the ring gets larger than, okay, on a Turing machine it will run, or whatever, on a random access machine it will run different. Okay, so here's an outline of how the proof will go, how the algorithm go. We reduce max2 CSP on n variables, defining a maximum weight triangle in just a huge weighted graph. Okay, it will not be d to the n size, obviously, but it will be huge. Okay, we reduce this weighted graph to some polynomial collection of huge unweighted graphs, and then we'll quickly check for a triangle in each unweighted graph using matrix multiplication. So that the triangle result only holds for unweighted graphs. So this reduction is necessary. And that's it. I mean, the algorithm is actually, in retrospect, really simple. And I hope that will be clear. Questions? Yeah. Okay, so first, I'll show how to detect a triangle. You can count the number of triangles quickly in an unweighted graph. So let A sub G be the adjacency matrix in the graph. And the observation is just that the trace of A cubed is non-zero if and only if the graph contains a triangle. And moreover, the trace is 6 times the number of triangles. And the reason it's 6 times is just if that's the number of walks one would take, one number of 3-step walks one can take on a triangle. 3 possible vertices, and you can go, say, clockwise or counterclockwise. So. Okay, so namely the II component will be non-zero if there's a triangle that includes the vertex. So the algorithm for triangle detection is totally straightforward. You just matrix multiply AG with itself twice, examine the diagonal. And this just takes as much time as matrix multiplication over a ring. So one open problem I'd like to mention at this point is, can a triangle be found or detected faster than doing matrix multiplication? Because we only need to really check if the trace of this huge matrix is 0. So while we can't have access to the entire huge matrix, we can think of it as a black box. And we could feed vectors to it and get some back. And this feeding would only take n squared time. So, I mean, it's possible maybe you could feed some random vectors to AG, compose it 3 times, and then somehow estimate with a trace. But the problem is that the known tricks, or the tricks that I know for estimating a trace, don't work here because the variance is just simply too high. Okay, just to warm up to the result, I'll present it for max cut. It's fairly natural. So we're given a graph G with set V vertices. We partition the vertex set into roughly 3 equal parts. So without loss of generality, we'll just assume that the number of nodes in is divisible by 3, and this is all nice. So we then enumerate all possible cuts for the vertices. And so that this total number of these different cuts, there's 2 to the n over 3 for each one, and so we have 3 times that if we look at each partition. And so for each vertex, what we'll do is we'll actually just say whether or not V goes on the left side or on the right side of cut. Okay, now we make a complete tripartite graph G prime, and it will have this many vertices per part. And the idea is that each part corresponds to these parts, and in L sub I, the ith part of this G prime, we have a vertex for each cut of the original. Okay, vertices and edges will have weights. The weight of this vertex will just be the value of the corresponding cut. And if we have 2 cuts, but coming from different partitions, so I is different from J, the weight of the edge will be the number of edges with one endpoint in, say, the part P1, P sub I, the other endpoint in Pj, but they cross the cut C and C prime together. So C union with C prime together is a cut for the union of PI union PJ. So is it clear what this means? I can draw a picture if you like. So we have let me make this bigger. So we have a piece of I, and we have a piece of J, okay? And let's say the cut we're looking at, so this is left and this is right. Okay, we have some edges crossing the cut that are within PI. We have some edges crossing the cut that are within PJ. These are counted in the weight of this cut, of the cut vertex for these. Now the ones that get counted in the edge are these. The ones that cross from, say, the right side to the left-hand side, but go from a vertex in piece of I to piece of J, and the ones vice versa. So those are the ones that get counted there. So this is the weight of an, so the cost of these edges, the number of these edges, is the weight of the edge for this cut to this cut. Sorry? And this is the weight of the vertex. So this is a cut C prime, this is a cut C. The weight of C prime is these cuts. Okay. Okay. So notice it just restricted on this graph, where if we sum up vertex, vertex, edge, then we have exactly the cut for this subgraph, the cut value for this subgraph. So, okay. Is this understood? Okay, here's just a very simple example, and it probably doesn't drive the point home as well enough as this picture. But so here we have this a 3-vertex graph, and here the vertices and the G prime will have weight 0 because we only have one vertex, so there's not any cut inside, so to speak. So the dashed and the bold triangles will represent the optimal cuts, which is just putting B on one side and AC on the other side, like here. And we have these weights, essentially if they have an edge, and they're on opposite sides. So I left out some 0 value edges here. Sure. So from G, the number of possible cuts for B is to put B on the left-hand side or on the right-hand side. The same for C and the same for A. All right. Now, so a one edge is whenever I have, say, A on the left-hand side and B on the right-hand side. That would correspond to a cut. So in this subgraph here, if I put A on the left-hand side, B on the right-hand side, it's exactly 1. Okay? So 1, 1, but these are on the same side, so it's 0. 1, 1, but these are on the same side, so it's right. So these just correspond exactly to the natural. Okay. So I suppose it should be clear, maybe, that triangles in G prime correspond exactly to entire cuts in the whole graph. So the goal is concrete, to find a triangle in this G prime. The total sum of vertex and edge weight is maximum. And the claim is that the resulting cut will be a max cut in G. So cuts in G are in 1-to-1 correspond to triangles. Let W be this weight function we defined. We're maximizing this summation here, sum of weights plus the sum of edges. But what do these weights correspond to? So for C sub I, it's the number of cut edges within this induced subgraph, say P sub I. And this edge, as we said before, is the number of cut edges between subgraphs, P sub I and P sub J. So for every edge crossing, say, the entire cut, so there's another one in the final triangle solution. So for every edge that crosses the cut, there's some either vertex or edge that captures it. and it's counted in the sum. So it's either contained in one of these or it straddles one of them. And this just follows immediately from the fact that the edge has 2 endpoints. This is nothing. Okay, so how to find a triangle in this graph? Because the cool triangle algorithm will only work for unweighted graphs. Well, there's a straightforward solution. You just try all the possible weight assignments for the triangles that you would like. So we pick integers k, which is supposed to be some cut value we would like to achieve. And we pick 6 integers so that sum up this cut value exactly. An interpretation of these is that, okay, whatever triangle vertex from L1 I get, say the first list of cuts, it will have weight I1. The triangle's edge from the first list to the second list will have weight I2, and so forth. And the total weight is this constant k. So that's what the interpretation of such an assignment would mean. So for each weight assignment, we have an unweighted graph where the weight of an edge or vertex is, well, so basically the edge or vertex is in the unweighted graph if and only if its weight is exactly what the assignment should be. So we can just go through all these possible assignments. There are, like, well, I guess into the 7 here, actually. And for each one, we get some graph. We just can test whether or not that graph has a triangle. And we just find the maximum k such that we still can find a triangle. And that's the algorithm for max cut. So are there any questions at this point? So now I'm going to generalize it for an arbitrary constraint satisfaction problem. And the idea is that you just set up the huge graph just as before, but you have a different weighting scheme. And that weighting scheme depends directly on the constraints themselves. Okay, so I'll define this mapping. It's like we'll just say what parts are responsible for what constraints. So a part P sub I will be responsible for a constraint C if all the variables that that constraint refers to appear in that part of variables. And a pair will be responsible for a constraint if there's exactly one variable for the constraint in one part and another variable in the other part. Okay, since all constraints have at most 2 variables, this is a well-defined map in a set of constraints to 1, 2, 3, and then the possible pairs. Okay, now we define a weight function on the nodes and the edges just as before. And the max cut, you'll see just a simple special case of this. So we have a vertex being in, say, the list L sub I, that has weight, the number of constraints such that the part P sub I is responsible for that constraint, and the corresponding vertex, the assignment, we call all different assignments in G prime, that assignment satisfies the constraint. And similarly, we just, like each edge gets sent to a weight that counts the number of things it's responsible for that its assignment also satisfies.
But what if you did complete 4-part type?
Yeah, you could do a complete 4-part type. But the problem is, so I presented it like the triangle because the 4-part type doesn't gain you anything. Because of the best known algorithm for finding a 4-clique, a 5-clique isn't any better than finding a triangle. So the problem is that yes, you can, but basically what this reduction does, it reduces it to a larger graph in which you're finding a triangle, and finding a triangle is equivalent to finding a k-clique, say a 4-clique in the original graph. So you just reduce it to the triangle case again. So that's why it's just the triangle. But yeah. No, please. Are there any other questions about how this about how this thing works. I mean, I hope it's totally clear, but I may have been looking at my slides too long.
For C3 is equal to K3, and that's not the case for 4.
Yes, that's true. So, well, but you can still do the same. You can still do the same thing in principle. You could have constraint. You could have finite clique, and you try all weight assignments for the different ways to pair them up, and oh, right. But the 4 cycle won't work because you have.
Right, but that's what he said.
Oh, okay. Right. I understand.
Well, also when you raise a matrix to the power 4, you can get going from one vertex to a neighbor back and
yes. Also, for even walks, you can have a problem as well. But yes.
The weight on the edges is that the way that what you actually get on the trace is the weight that you want.
Well, so let's think of what happens whenever. So the way, I mean, when a matrix gets multiplied, and we have weights on the edges. So there are a lot of different. I mean, an entry will just say sort of like the sum of the weights of each walk, right? So.
So you get towards that number that you get on the trace more meaningful to you.
Perhaps. You could. But I mean, it's possible. I don't. Okay. So.
there is a non-Euster's weak algorithm for finding cycles in graphs. And they already,
yes.
Now, one of the presentations, in the middle, they had like several improvements.
Yes.
Somewhere in the middle, they used matrix multiplication and they got rid of it.
Uh-huh.
So did you look at the latest one, or?
So, I mean, right, so you mean the cycle finding out, right? Yeah, cycle, so that's for at least cycles of at least even length, right? I mean, I'm pretty sure that for cycle, so for finding a triangle, finding a 3 cycle, the best is known as matrix multiplication. Yeah, bigger cycles get easier, but cycles won't suffice in this setting. Well, it's possible. Maybe you could choose some nice partition of the variables so that the cycle would suffice. But it seems to require some stuff. Thanks for all the questions. Okay, so this is slightly more formal development of how we go from the weighted problem to the unweighted problem. So we want to count how many assignments will satisfy exactly k constraints. So we can actually do this with 3 weights by putting by just trying all the possible weight assignments on edges. So I don't know if this is what you were thinking about, maybe, but so we can just try triples of weights. And what we'll do is we'll put an edge in this new unweighted graph if the weight of, say, vertex, so from V1 to V2, one's going from part 1 to part 2. We'll just put a weight if the weight of the second vertex plus the weight of this edge is equal to that exactly. And similarly, for, say, the third vertex, for this one, the weight of the second and the third is equal to that exactly. Okay, so we only include edges, the weight across it is a certain quantity, and here we still have the sum that we want. I mean, for something, I mean, the sum of these will be the sum of a triangle of that certain weight. So a triangle in some such G prime has weight k in G prime, and moreover, any triangle with weight k and g prime appears as a triangle exactly once, because there's exactly one such weighting for them. So the final algorithm is we have a set of m constraints C, 2 constraints. We have some parameter k, and we want to find the number of variable assignments that satisfy exactly k constraints. Okay. So the algorithm is quite simple. We just try all of the that will sum up to k. Okay. Then we construct this undirected graph. This is actually g prime. Sorry. G prime based on these weights, which has an edge if and only if the weights of its vertices are appropriate. And we set the count to just number of triangles in that particular graph. And we just do this and return the count, and that's the number from what we said earlier. So here there are just m cubed triples to consider. And this much time to count the triangles, because this is, well, order this is the number of vertices. And so we have a 1.732 roughly, given the current best algorithm for matrix multiplication. So notice that this will require a lot of space using matrix multiplication algorithms that I know of. And so another good question is whether or not there's a polynomial space improved exponential algorithm. It would be very nice to somehow, I don't know, maybe find a triangle in log space. You know, the vertices. Okay, so I'll just talk about some further directions one might take this kind of complicated merging approach. How can we solve more general problems with this thing? We just solve 2 constraint problems. Can such as kind of split, so splitting into partitions, listing assignments, and then merging. Can such a tactic work in general? So explicitly, is it possible to solve, say, C and F SAT, just a general SAT problem, significantly faster than using this? So yeah, if you tried in your head to immediately generalize the KCSP, you have hypercliques and a hypergraph. Actually, I don't really know much about algorithms, like what the runtimes of algorithms are supposed to be like. That would be also an interesting thing to try to do, to send this idea to next CSP. So a few promising approaches to this kind of direction. They involve reductions to polynomial time solvable problems that are also interesting in their own right. So they're polytime solvable, just like finding a triangle. But if you have non-trivial algorithms for them, so just something better than just the obvious algorithm, then there exist improved algorithms for other hard problems by reduction. So, for example, there's a problem that I call cooperative subset query. So what is subset query? Usually in a query problem, database query problem, you have some database of objects, and you have some adversarial list of queries about the database. And depending on the dimensionality of the objects involved, you can often get very difficult query problems. In particular, this one called the subset query problem, where the database, the objects here are sets over some universe. We want to build a data structure that will efficiently answer queries of the form, is Q a subset of some set in my database? So Qs are also subsets of the universe. We just want to know, is this a subset of something in the database? So this is a special case of partial matching, where you want queries with wildcards. So you're looking for this in a database. And this problem was studied by Rives in the 70s, but not much is known about its complexity, beyond just sort of the obvious things one might try to do. And there's a paper in the ICALP 2003 by Charakar and Dick Panagrehi about making some slight incremental improvements on this in terms of algorithms, but still not very much is known about the problem in general. So all solutions that have been discovered so far They either require essentially searching the whole database or just storing all possible subsets up front, roughly speaking. So you can store all the possible subsets up front in some, say, bit vector. You have 0 if nothing is a subset of this particular set, and a 1 if something is. So now your query is just constant time, really, just, or whatever. Access the vector and see if it says 0 or 1. But this is a ridiculously large space bound, so either one of these is not desirable at all in general. So we're going to look at the following weaker version of the problem, where all of the queries are given to us up front. So we have two collections of subsets over some fixed universe, and we want to find a set in one and a set in the other, so that the first is a subset of the second. So all we want to do is just determine if one query will be a yes answer. And intuitively, this ought to be easier since we can just sort of pre-process, and all the query information we'll ever see is known to us up front. We could somehow customize our database based on these queries and determine something. And so here's the problem. Just stay it up here again, just to keep in mind. Now, of course, this problem is trivially solvable in this much time. Just trying all the triples and then test. Or trying all the here. So can it be done any faster? Now, if you believe that CNF-SAT doesn't have an improved exponential time algorithm, say there's no such epsilon such that you can solve CNF-SAT and to the epsilon in, then you should not believe this has a faster algorithm. And this is the reason. So if you can solve this cooperative subset query problem in slightly less than quadratic time. So K here is a maximum size of either domains. And we have just some function f on D. If we can solve this problem in sub-quadratic time, then a very simple argument shows that CNF-SAT is also solvable in something just slightly, this will be slightly less than 1 depending on epsilon. Again, here, so in the second part here, n is the number of variables, and n is no constraint, the number of clauses. So it could just be whatever. I mean, the idea is, you'd like to say f to be a polynomial. Okay, it's a very simple argument as to why this is the case. Okay, recall in CNF-SAT the constraints are clauses. And they're ors of literals, which are negated or non-negated variables. Suppose we index the clauses by C1 through Cn. Okay, now we will partition the variable set into two sets now. Size roughly n over 2 each. And as before, we'll make lists to the n over 2 assignments. Now, we'll associate with every assignment on the first list a set, where we put a constraint in the set if this assignment does not satisfy it. Okay? For all assignments in the second list, we'll make a set where constraint is in this set if the assignment satisfies it. Okay, now the question is, if everything, so basically if there's a set in the first and a set in the second, such that this one is contained in this one. So what does that mean? Intuitively, it means that every clause that's not satisfied by this assignment gets satisfied by this assignment. So these partial assignments. So the claim is just the clause set is satisfiable if and only if the subset query instance has a yes answer. Okay, that's the end. I mean, yeah, that's all I have.
I talked about calculating the permanence exactly, and better than 2 the time algorithm. Actually, I don't know that that's how it is. It's being the primitive 0 1 matrix. So
Hasn't it been become harder than NP?
pardon me?
Isn't the problem harder than NP?
Yeah, but you could still maybe solve it in time, I don't know, 1.9 to the n.
Yeah. So I know that there's some algorithms that are like less than 2 to the m, where m is, say, the number of non-zero infrequent matrices. But, I mean, okay, so if you had like a very sparse matrix. And this is phi. So there are some algorithms for something, for counting number of solutions to a monotone two-set. So in other words, like, basically, they're all positive variables. You just want to count the number of solutions. So this is just that, but I don't know if like a, like a 1 by.
I'm just curious, in one of the beginning slides, you had a time of something like 1.33 to the n to solve 3 SAT.
1.324. So in 99 there was a paper in Fox by Schuning. It shows a random walk algorithm that. Yeah. Yes, and in the same, so in the journal version of that paper, have one like 1.481. So the algorithm that's 1.324 to the n, that's the
randomized. I think that still is the best deterministic.
I think there's like another one, but yeah, these are all number races. I think there's like one. Oh, sure. Okay, sure. I think that's the only randomized one. Okay. All of these are deterministic except for the. Any more questions about this slide? I mean, while it's there. Yeah. So to be honest, there's another improvement on that one. It's like 1.475 to the n. Yeah. For the deterministic versus randomized algorithms is the issue. This is a randomized algorithm. Other questions? Thank you for your time.